So let's welcome the first presenter, Tim Ahern from Earthscope, presenting Rapidly Changing Metadata, a project to add fair metadata to existing standards.
Thank you very much, and I'm really Earthscope emeritus. I don't get paid, and I'm actually retired. But anyway, it's still active in a couple of projects that are being carried forward in the International Federation of Digital Seismograph Networks, a mouthful, the FDSN, and one of them is called Rapidly Changing Metadata. As you know, the FDSN is very based upon SEED as a standard exchange format, but there are certain use cases where you really can't capture all of the data to make, all the metadata to make it understandable, reusable, all the principles of fairness in data. And so we have some of those use cases, and we found a solution that was relatively easy to implement, but yet not yet incorporated into Station XML, which is the major way of exchanging metadata. The SEED format's been around for a long time, almost the same time as the CTB-TO formats, and there are certainly bridges between the two formats now. So it captures most of the seismic data in the world. But the problem with SEED and CTB-TO formats is that they assume more or less always stations that don't move. Or at least if they move very slowly. So I'm going to describe in this talk a method called RCM, not a very clever name, but it's about rapidly changing metadata. It's a lot more than positional data. It can be things like when sensors change gains rapidly, several times a minute or seconds even. I spent 31 years at the IRIS DMC, and we had several use cases where frankly it was very difficult to fit them into SEED efficiently. So GeoCSV grew out of a project that was funded by an NSF program called EarthCube, and it's basically a comma separated value way of capturing metadata, but it has an inference about the type of geological geo information that makes sense to use in many domains in our sciences. So the motivating factor that drove us in this direction first was a program called Mermaids. You may know about them. These are gliders. They just float in the ocean, follow the currents. They sink down to 1,500 meters typically. They listen for P-wave arrivals in the ocean. When they sense one, they rise slowly to the surface, drifting in the currents as they come up. You don't really know where it was at this point when the P-wave was detected. And they surface, they reconnect with GPS time and location, and then they transmit a data window around the P arrival. And then they slowly drift back down, listening for the next event. Oh, I'm sorry. The figure on the left shows, on the right shows the position of one sensor in the South Pacific for 4.5 years, just drifting around. The oldest data are the red ones, and the dark blue are the earliest ones. So you can kind of see it stays confined in kind of a 10-degree location in the Pacific because that's what the currents decided to do. They're not controlled at all. These things go up and down, they're changing location, and to use them for event locations and things like that, you need to know where that sensor was when it detected the P wave. It's a lot of metadata that's changing rapidly in this example, this use case. So GeoCSV is pretty straightforward. It's not complicated. That's part of the beauty of it. It's constructed by a series of GeoCSV headers. I'll give you an example of those. And also GeoCSV column headers. So they identify the data that are in the cells below it. We've identified, based on my history at IRIS, several things that apply to rapidly changing metadata. The first one is you need an identifier to capture what kind of seismogram it is. So in SEED format, it's the network station location channel identifier. Hopefully some of you are familiar with that. And you need starting times and ending times as well. So that's one that is almost always present in a GeoCSV file. But frankly, the others are not necessarily present. You put them in, those sub-elements, the ones in colors, if you need to. For instance, the position element is an element that contains things like the latitude, longitude, depth, or elevation above the surface of the Earth. There are sensor and gain elements. We have data, back when I was at IRIS, we had data where the gain was changing rapidly. I would turn up the gain when it's on an event, but it tried to stay on scale for large events, and the gains would change. An example of that was the H2O observatory. It was on a telephone cable halfway between Hawaii and California, and they were constantly changing the gain. Very difficult to keep track of the metadata. We did it, but it was very inefficient. Or you could have timing elements. Applies to mermaids. You know the time exactly when it's at the surface, and you know it at the next time it's at the surface. But when it was down below, you have to interpolate somehow. So, and it's not always just a linear interpolation. It depends on how you want to do it. So there's timing elements. Another one would be OBSs. They drop to the ocean floor. They're usually not oriented. Their azimuth is unknown until you measure it after the fact. So that's an example where you can actually document it and include it in the seed format. Another nice thing about GeoCSV is it's flexible and extensible. You can add elements if you have a use case that isn't covered by one of the existing elements in the colors. So here's an example of GeoCSV header. It's very simple. It's a data set. It tells you it's in GeoCSV format. It's created on a specific date and time. It has a very long description. If it's a pound sign to start, you can put anything you want to in there. So this is metadata for the drifting mermaids, hydrophones, and then there's a link to Earthscope Oceans, the website. You can provide attribution. For instance, the algorithm that calculates the position while under the water in the mermaid case is quite complex, but there's a reference to it, what version of AutoMade, that's the algorithm, was used, where you can find it, and even a DOI to it. So you can document it, you can reproduce the results if you care to. Same thing for the MATLAB reader versions used for some of the tools. There's a line talking about how they converted the pressure measured with the pressure sensor at depth to a water depth, and that's the conversion factor. There's also frequency responses of whatever the sensor was underwater, and again, it's a link to something in the nominal response library at IRIS. And that's the GeoCSV header. It's pretty understandable even if you've never seen it before. This is an example of the column identifiers. It has things, I'm going to start at the bottom, method or the identifier. For instance, it's the latitude. You know what that is by just reading the word. You know how to use it. You know it says it's represented as a float, and it's in degrees north, which is the FDSN convention for it. So along with all those others, you basically can identify what the data columns contain below it and what the units are and any other pertinent information. Here's a sample, which I'm not sure how well you can see that. I highlighted, there's the GeoCSV headers, there's the column headers, and then I highlighted 3 bands there. I can't read them from here either, but those are actual measurements. So that was when it was at the surface, it knew the time exactly, or GPS time well, and it knew the position. And all the white ones would be interpolated values. It also has, one of the lines shows the actual pressure reading from the instrument, and then again, I think the other one was, can't remember. I think it's an AutoMade, one that was calculated. Another example where you might use these things, where we have a lot of deployments on glaciers and ice shelves, solid ice moving somehow, and it changes with time. It could also be a landslide. And this was an example where there were a lot more measurements of metadata for this, and this was over, I believe, about 6 years of data, and I just pulled out 1 sample per year. But the sensor was changing in elevation as the ice rose and fell, and this was on the ice shelf. And also you can see that it changed about 10 degrees in latitudes and longitudes, so quite a range. But it's a way to standardize it, capture it, include it with the seed data, or provide links to it, rather than the way it's documented now, which is in somebody's notebook, and you have to call them and try to get that information. Here's one for the offshore deployment off the west coast of the United States. And again, 3 groups determined the orientation of those sensors, and they aren't the same. based on, earthquake arrivals from different directions. At least this is a way to document them. You only include the rapidly changing metadata elements you need. If you consider seismometers on a glacier, which was one of my examples, it's just the position element and the orientation element that are really key factors. So you don't include the things that aren't changing. So we looked at GeoCSV information available, and we came up at this point with only one of two options, the way to include it. Mermaids are voluminous. There's a lot of metadata generated. They're very large. My belief is they're too large to include in a station XML or an XML variant. They're just too big. So my recommendation to the FDSN meeting last week at IASPE was that we support two options. One is a link that provides a pointer where you can find the GeoCSV file. In the Mermaid case, those are large files. Okay. And if they're small enough, for many use cases, it would be small enough where I think the logical thing there is to small GeoCSV files, just append them to the end of the data seed in a standard manner. It's up to the user to choose which option, one or two, actually including the rapidly changing metadata directly or having a link, a pointer to them. So in summary, GeoCSV files have enabled the projects that capture RCM in a straightforward and efficient manner. It turned out it was very flexible for all the use cases that the Mermaids have. It's probably the most complex case I could think of. We were able to find a way to include it in the GeoCSV files. The format really enables fairness of the data because it identifies what the fields are, what they contain, and even the units of what the measurements are. Not always true when you go to a person's lab notebook. It should be, but it's not. It's flexible. New elements can be added as needed, as I said. It can document actually observed data or data that come out of a complex algorithm. So there are methods of doing that. It's an easy way to capture objects that make the data fair, which is a big push in most of the world now. Europe, I know, and certainly the US. And as I said, it can be included directly into the station XML file in a straightforward manner, or it can support external links. This requires changes by the FDSN working groups, but I think it met with positively received, I think, in IASPE last week. So that concludes my talk.
Thank you very much. Now it's time for questions. Okay, maybe I have, yeah, please. There's a microphone.
Thank you for your talk, and I think it's a much needed development.
Thank you.
Could you comment a little bit on how this could be implemented for the CTBTO? Would you have some knowledge?
Yeah, I'm not the best one to talk about it because I lived in the world of seed formats there, but I don't think it's hugely different. You need somebody that understands their formats better. By putting it into station XML files, the CTBT could do the conversion. I just don't know how they would map directly. And maybe there will be difficulties. Maybe they need to adopt a way to link to a GeoCSV file. The point is, it's not that it's a firm, rigid format, but it's something that's pretty flexible, and it's a mostly standard way of capturing all this metadata that's sometimes just kind of lost when the PIs disappear, people that knew about the data set. So don't know about the exact mappings.
Maybe the option of the pointer could be a good solution in one of the tables.
The problem with it is the pointer points to a file that has to exist somewhere, and so the persistence of that becomes an issue. That one pointed to a data center in the EarthScope data center, and what if the EarthScope data center disappears? So it also needs to add some sort of persistence. It needs a persistent identifier, I think. And I didn't worry about that aspect of the problem, but it's known. Thank you for your question.
In the back.
Hello, I'm Andrew. Thank you for your presentation. regarding your topic on the datas that are entered in the CSV file, especially using the Mermaid device. I was in a seminar above for waveform technology, so using DAS and the cables below, and they believed sometimes the data is too huge to be kept. Could you explain more on how this two can connect? So this GeoCSV and now the cables that DAS use for seismic data collection.
Yeah, thank you for your question. I'm not a DAS expert. I think the volumes that they're talking about are so large, but it's actually the derived time series data that are very large. It's a slightly different problem than the data that the metadata that describes the data. I also know that the DAS have very standard formats that have been used by oil companies and academics now, and it's a very different format than SEED. So again, I'm not an expert in DAS formats, but the concept could still be used, assuming that the metadata is changing rapidly. Is it in DASs? I don't know.
Not so sure myself, but thank you so much.
Yeah.
Okay.
Okay. Thank you very much then. Thanks.
Thank you.